Welcome to the SeaWorld Research and Rescue Center. I am Dr. Elise Marquis, and I thank you all for attending this new science talk of the 2025 series. I'm standing here because we have a new podium, but I don't know if you can see me. It's not been designed for me. All right, I'm gonna stand here then. As you know, this series of Science Talk at the Center is developed in close collaboration with the Environment Agency Abu Dhabi, the Emirates Natural History Group Abu Dhabi, the Natural History Museum Abu Dhabi, and Nautica Environmental Associate. And on behalf of the Center and all our partners, please receive our best wishes for this holy month of Ramadan. And it's a true pleasure to welcome you to this exciting science talk titled Dinosaurs, Sea Dragon, and Aeroplanes. And frankly, if there was a competition for the best science talk title of the year, this month's talk would undoubtedly be the frontrunner. And I don't know if you are the same as me, but I'm dying to know what's beyond that title. And we are very lucky tonight because as part of our partner on that Science Talk series, we are very, very happy to host Professor Phil Manning, the Director of Science of the Natural History Museum Abu Dhabi. And because I don't want to be talking too long because I want to know what's behind that title, I'm not gonna continue further before. I just want to give you a few points. I hope everybody had time to break fast and to have a good iftar meal. I will ask you to avoid going in and out of the room. Make sure your phones are off. We don't need any phone tonight. And please enjoy. I'm expecting a lot of questions at the end. We will take the time together. We will sit with Professor Manning and we will take your questions. So just keep them in mind until the end. But now, I want to introduce Phil Manning. And actually, it's quite a long CV that we have when we are looking at his short bio. But I'm extremely honored to call on stage Professor Phil Manning as our unique speaker tonight. As I said, he's the Director of Science of the Natural History Museum, but also Phil retains his Chair of Natural History at the University of Manchester in the UK. He started working at the Natural History Museum Abu Dhabi project as a scientific advisor in September 2020 and joined the team full-time just last year, actually. His research has focused on different facets of the evolution of life on Earth, which he and his team interrogates using new imaging techniques and technology borrowed from physics, biology, chemistry, engineering, and computational science. A large part of his research has developed the use of synchrotron light to map and quantify the chemistry of life from both extant and extinct organisms. I'm not doing any favors to that, so he will explain much better than me what that means. But you will see as well that Professor Phil Manning has been very active in trying to communicate and educate and share his passion about what he's doing. He participated in different documentaries that you will most probably be able to find online with the National Geographic Channel, with Discovery Channel, with CNN, with BBC, and so on. All right, that's it. I'm stopping talking. Please welcome on stage the Professor Phil Manning.
Thank you. Thank you. Good evening, ladies and gentlemen. That's right. Thank you very much for a very kind introduction. And good evening, ladies and gentlemen. I'm going to tell you a story this evening. hopefully. Does the slide come up automatically? Yes, it does. That's always a relief. Otherwise, it would be a very short talk. No, but it wouldn't actually. I'd have quite happily gone into Q&A mode. But science is about stories. The history of life is written in many ways, but it's a beautiful, rip-roaring story that tells us so much about life in the past, but it also informs us about what's happening today. And as so many of these wonderful three-act plays does, it can tell us something about the future as well. So I'm going to let you explore a little bit of my strange world, which I've occupied for a few decades now, but it's one which I absolutely love. And certainly to the younger members of the audience today, I would say, if you choose a career, choose something where you really love it. Because if you do, you never work a day in your life. Now, I'm going to start by where I am at the moment, because I can't not mention the sort of elephant in the room, or as you cross over the bridge to Abu Dhabi, you might spot Team Lab just immediately next door to the bridge, but we're the next building along. There's a wonderful team of people working at the Natural History Museum Abu Dhabi who I'm going to embarrass a little bit now, because I know there's one or two people here from the museum, and I know there's many of you might have questions about the museum later. And first, I'm going to be really cheeky and introduce our director. It's Sir Dr. Peter Kiergaard, or Kiergaard, as you say. But Peter, please, would you like to stand? This is our director at the museum, everyone. Thank you. But there are many other people here. Now, please, everyone who works at the Natural History Museum Abu Dhabi, and that includes you, Mark, please stand up, because then you'll see basically that is my audience. Please, everyone, stand up. Now, what I find remarkable is that how this building has gone up so quickly. But people keep using this phrase, and I'm beginning to understand it. It usually goes along the lines of only in Abu Dhabi, because it moves so quickly. I say, how can we do this so quickly? It's only in Abu Dhabi. Okay. Many of you might have come across this character, and this is just one of many. The museum takes you on a journey from 13.8 billion years ago, from the formation of the universe, right the way through to the formation, the genesis of our own planet, and it charts the history of life on Earth. A great story. And of course, the Coca-Cola of life on Earth for many people is these strange, huge creatures, the dinosaurs, of which this character is probably one of the most famous. Ironically, it's not known from a complete skeleton. In fact, there's only maybe a dozen which are more than 50% complete. But, of course, only in Abu Dhabi, you get one of the most complete ones known to science. And this one's called Stan. It's quite a stunning fossil. And it's already been announced, I'm not telling you anything new, but there'll be this specimen and many other wonderful objects, charting not only the evolution of life on Earth in the past, but also that of life on Earth today. And we're hoping to open the doors of the museum when it's ready. So you have to wait for that announcement. But I really do look forward to welcoming everyone here to this wonderful museum. But you've sort of seen the backs of the heads of some of the team. But I'd like to highlight one particular person here today. Now, I haven't got my singing voice on me, but it just so happens that one of our team sat here. Thank you. Happy birthday, Pavel. He assures me he's 21 each year. No, but I'm going to take us back to the world of some science. I'll start off with my sea dragons. I apologize. I did get the dinosaur in first. Now I got some sea dragons. There will be some aeroplanes, I promise. This is one of my favorite scientists. He was a brilliant French scientist, Georges Cuvier, who invented something that most people would probably want to hide, this idea of catastrophes, extinctions. Without extinction, which he invented way back in 1796, it was interesting how he discovered it. They were digging up the bones of an elephant. Where's Mark? There's Mark. Mark Beach, our in-house expert on all things tetratetrabelodon and unpronounceable. Now, but there was another type of elephant, not the four-tusked ones we get in the Binuna Formation, which Mark works on, but there was these creatures called Paleoloxodon antiquus. These are the straight-tusked elephants. They were digging them up from the plaster and Paris mines of Montmartre. And what was remarkable, Cuvier recognized that they were different. Didn't look like anything alive on the planet today. So he had to come up with a mechanism to explain that. And he brought us a mechanism without which Darwin could not have written Origin of the Species. This mechanism, of course, is extinction. Because if we didn't have extinction, it could get really interesting doing your weekly shopping, having to push mammoths, straight-tusked elephants, and the odd dinosaur out of the way. Sometimes extinction can clear the way for other species. So it's a very important mechanism. He also based it partly on the jaws of a marine reptile. This is an animal which once lived on land, but its descendants evolved to live in the sea. And these are things called mosasaurs. These are like a giant lizard with paddles. These remarkable creatures were first discovered back in 1770 in Maastricht. But Napoleon borrowed them when he was on one of his jaunts. The French Revolutionary Army actually took them back to Paris, which has upset people a lot, but I won't go there. Anyway, but these jaws, he looked at them and realized that this was a reptile, but it was living in a marine environment. It didn't fit. So this mechanism of extinction allowed him to explain these creatures existed. These ideas were then carried on through into the 19th century. I've got to be careful now because one of my esteemed colleagues in the room is an expert on the history of science, so I've got to be very careful. But one of my heroes is Mary Anning. Now, anyone in the audience, if I say the first word of this tongue twister, can someone say the next? She sells seashells on the... What's the next verse? That's very good, almost there. So she sells seashells on the seashore, but the shells she sells were once seashells living on the seafloor. It's talking about fossils. She was selling fossils and making a living out of it to anyone who would buy them. And at this point, it was what they often call the heroic age of geology. People were buying them and filling museums around the UK. And the Natural History Museum, or it was then the British Museum of Natural History, was in its infancy because it's still not even formed when she starts collecting her fossils. But much of the fossils she collected did end up at the Natural History Museum in London as we know it today. But of course, Buckland brings us dinosaurs. Everyone thinks he's the one who gave us Megalosaurus. He's a naughty boy. He didn't. In 1818, another gentleman by the name of James Parkinson, he worked on Megalosaurus, but he did such a dreadful job of describing it. Nobody cites his work. The only thing we remember James Parkinson for is sadly the disease which bears his name, because he discovered that. But it was Buckland who gets the fame in 1824 for his Megalosaurus, and Mantell, who actually had already sent some teeth and bones to Buckland for advice. I think Buckland was a bit naughty and scooped him, but there you go. He did send the teeth, which end up being a creature called... I can't do it. I can walk up, can't I? I like this. These teeth here... He bumped into another gentleman at a museum, the Hunterian Museum in London, who was studying marine iguanas, strange lizards that you see on the Galapagos Islands today. And they're strange because not only do they live partly in water, but they graze, they're plant eaters. They eat seaweed and so on. And their teeth are adapted to do this. And when Mantell bumped into this gentleman, he said, "Ooh, I like your teeth. Well, not the gentleman. You go, "Ooh." Didn't do that, don't worry. But he looked at the teeth this gentleman was looking at the iguana. He said, I've got some fossil ones that look a bit like that. So what do they call this one? Iguanodon, thank you. Yes, that's bingo, you got it. Literally meaning iguana tooth. But of course, this all gets pulled together by this rather scary-looking gentleman. Now, I often describe Richard Owen as a suspiciously clever academic who seemed to do incredibly well on very little information. He famously described a whole bird of an extinct group called the moas from New Zealand, not the ones you push cutting grass, but, well, these probably did cut grass quite well. But anyway, but these giant birds, from a single bone, he reconstructed the whole animal, or so the story goes. Some suggest he had more bones and just didn't tell people. There you go. But what did Owen bring us? Owen brought us something which has remained in the public psyche for decades, centuries: dinosaurs. He came up with the term he published it in 1841, but he had a meeting of the British Association for the Advancement of Science in 1840. There's no mention if he actually used the word or the name dinosaur at that stage, but in 1841 we have the invention of dinosaurs. Very simple. It was based on some characters that you see in the skeleton. And if you had these, you possessed these characters, you were a dinosaur. And if you've met my brother, he qualifies. No, but no. The thing is, the science of paleontology has moved very rapidly now. And to take you on this journey I'm going to do today, I need to explain some very basic principles. And that is, a body fossil, it's not just of bodies, but it's of physical parts, elements of the skeleton. It can include soft tissue if that is preserved as well. That's a body fossil. It's the actual remnant of the organism. Trace fossils are a function of the action of an animal, or even a plant. If a plant falls down and leaves an imprint of it, that's effectively a trace fossil in many ways. So there are trace fossils. There is a new fossil on the block, which is a chemical fossil. Sounds a bit bizarre, but chemistry, as in most science, is beautiful. Science is beautiful. We don't have to make it beautiful, it already is. And I'm hoping with some of the images I'll show you of the chemistry of fossils, you'll see why we can learn so much from using techniques to uncover the chemistry of life from millions of years ago. So let's talk about, this is the ideal scenario. This is what every paleontologist dreams of. These boxes are filled. So there's your life, animals all alive, then they all die together, they all get fossilized together, and we can collect 100% of them. And no, it doesn't work like that. What we usually get is a thin line at the end of what's left in our little container here, which represents what's fossilized. If every single animal that ever walked on the planet became a fossil, we'd be up to our necks in fossils. We're not. The process, or the earth processes which can recycle materials, do so efficiently that it's sometimes very hard to find even a single bone which represents a whole species. And if you think about that, if you think of how big a population needs to be to survive, to be genetically viable, there's enough of them so that they don't go a bit strange on you. But you need thousands of individuals in a population. And over several generations, you'll probably have millions of just one organism. Some fossils are known from a fragment of bone, and that's all we have. So it's, as Charles Darwin put it really beautifully, when you look further back in time, it's like a great library. The further and further you go back in time, the fewer books are returned to that library. As you get into deep time, you're left with the odd paragraph. Into deep, deep time, into hundreds of millions of years. It's the occasional word, maybe a letter, from which you've got to reconstruct those volumes of life, which lived millions of years ago. So it is quite hard to do. But that's why, bless you, that's why we're trying to use new techniques that help us uncover that. But I'm going to do a quick test on you now, a bit of audience participation time. And And please don't answer SeaWorld, that doesn't count, before I ask you the question. Where do you see penguins? SeaWorld. No, don't go there. Yes. Antarctica, thank you. So we're in Antarctica. Where might you see this funny little yellow-eyed penguin, though? New Zealand, thank you. Someone said New Zealand. You've got to be in New Zealand for those. They're wonderful little creatures. Right, this game goes on. How about this one? What is it? Anyone? What type of... Barn owl, brilliant. Where do you see barn owls? UK everywhere, actually. They tend to get around a bit. But this is actually a UK barn owl. We're getting the idea now. Where might you see an alligator? Florida, good. We're in the panhandle of Florida. And if anyone says to you, let's catch this 800-pound alligator, the answer is no. I couldn't walk for a week. Now, this one, where you might find a rattlesnake? There's quite a few places in North America, but where I'm digging dinosaurs, particularly, these are annoying me. Actually, I don't like snakes. I don't want to harm them, but I don't like rattlesnakes. They like coming to our dig sites. You put a tarpaulin down on your bones to protect them at night. And if you're not very smart in the morning and lift up the tarpaulin to take this cover off the bones, there's a rattlesnake there at your feet doing its dance. And you don't want that because they can spoil your day. Where would you have to be to see these? Now, this is a good one. Not Galapagos, but it is an iguana. It's a blue iguana. It's a strange one. It's called Cyclura lewisi. Anyone? Yes? Not Madagascar, but you are on an island, a very remote island. I managed to convince Manchester University to fund my research there for several years in winter, for good reason. Anyone else? Let's have a... Cayman Islands. Who said Cayman Islands? Well done. It is the Cayman Islands. They're only found on Grand Cayman. There was an amazing study done on these creatures because they were critically endangered. There was less than 200 individuals known. And there's this wonderful gentleman by the name of Fred Burton who realized this. He said, we've got to do something about this. We can't have these incredible animals go extinct. So he set up a breeding program where he looked at the genetics of every single one of these creatures and worked out which ones should be partners and which ones not. There's now over 1,000 of them, and they're re-releasing them into the wild. So they're off the critically endangered list. Isn't it funny? We tend to hear a lot of doom and gloom stories, but there are some fantastic stories of conservation success out there. This is one of them. And Fred did an amazing job. Where are we now? That's right, Liverpool. No, it's Knowsley Safari Park in Liverpool. But yes, Africa. Someone said Africa. You're absolutely right. You're getting the picture. Have you noticed how different these animals are as we move around? Where are we now? Mars is a good answer. I like that. But if there's life like that on Mars, yeah, maybe not. I should be asking, when are we? Because this actually is the late Jurassic. Now, the reason I'm showing you this now, just think about it. I've just shown you how life varies across the whole planet, depending where you are. So when you, as a paleontologist, study a point in space, that quarry that you go to dig up fossils, it's representative of one point on what was a global distribution of species at a point in time that your quarry only represents a fraction of. So when you're trying to reconstruct the past, it can be blurred by bias when you're collecting in a particular area. In fact, much of our bias is because a lot of the science of paleontology started in Europe, then North America, and has grown out across the world. But there's vast tracts on continents in the global south that have not yet been explored, where I'm sure there's young scientists here in the audience today. If you so choose to take this mission, there is phenomenal things for you to discover still. It's not what we know that's exciting, it's what we don't know. And for me, the science of paleontology and looking into our past has never been more exciting than it is today, because we've got new ways of studying these creatures. And of course, that palette of where life is in time and space changes due to, I think if you came to the tectonics talk here a few weeks ago, which was wonderful, we can see this global ballet as a function of the movement of continents relative to each other due to plates uplift and pushing apart in central oceans and this beautiful continental drift that we see through time. We can actually work out where the continents are through time based on a technique called paleomagnetism. So any magnetic minerals which align themselves to the north-south pole at any moment in time, you can take very careful samples which allow you to correlate that position where they're pointing north and south, so you can work out where that piece of land was way back in time. So I'm very pleased with plate tectonics because it means I have a very big field program. Sorry. And this is where the director of the museum is going, oh no, this is where he's asking for money. But that's one of the aspirations. It's not an aspiration. The Naturalist Museum Abu Dhabi is already exploring around the world. If you came here a few weeks ago to listen to Ludwig's talk, our curator of meteorites, he's doing work in Brazil, so I need to add a star on there, I'm out of date. But these are projects which are happening around the globe from various members of the team. And it's a very exciting series of projects because we're trying to just unpick so many of these lovely stories that we can hopefully tell here in the future. Now, one of those stories which we've been working on for a few years is based at the site we've been working up in North America. It's out west, and if you know Wyoming, it's not many people there. It's lovely. And Wyoming, about 150 million years ago, looked a little bit different. There was an inland seaway pushing in from the north called the Sundance Seaway, and the creatures I'm looking to dig up used to live on the edges of a floodplain feeding this inland seaway. And there's lots of bones there. It's depressing, actually. Having spent most of my childhood collecting fossils where Mary Anning did, actually, on the south coast of England, where I'll be lucky to find a scrap of bone. Here, you could blindfold me and you could find bone at this site. We nicknamed it the Jurassic Mile. It's in what's called the Morrison Formation, and it's rich with fossils. This is what it would have, well, might have looked like 150 million years ago, with your classic sauropod, long-necked, long-tailed dinosaurs. They're stunning creatures. These are truly the titans of the Jurassic. And I'm in awe of these creatures, speaking as an engineer, because this is a moving house. This is 30 tons of flesh and bone, which is, no pun intended, dynamic. Oh, come on, it was quite good. But these vast creatures really test our understanding of engineering. And they're made of materials the same as you and me. So by studying these creatures, we can possibly learn things about the engineering limits of the materials which we are constructed of. There was a field called biomimetics, which was quite trendy in the 70s and 80s, but people kind of forgot it. I don't know why. It brought us wonderful inventions. But I would argue there's a new field developing at the moment, and that's where I'll take you tonight. Oh, he's looking hungry. Let's move on. So this is where we're working. It's in what's called the Bighorn Basin. You're surrounded by mountains. What's really fun is we can see Yellowstone from our dig site, which I'm really hoping doesn't go off because it's one of the world's super volcanoes. We don't want that to go pop when we're in the field or any time. It's stunning landscape. This is the Vermilion Valley, which our dig site looks down to. And it's one of the classic areas where geologists who are at university in the US go to train on how to map where rocks are, where they are in the field. And it's a beautiful area to go to. It's absolutely stunning. But we go there at silly times of year, because this is when we first took over the lease for the land that we were digging dinosaurs at the Jurassic Mile. And I would point out the numbers on the left there are Fahrenheit. So anyone who can do the calculation, what's minus 9 in centigrade? When it's Fahrenheit, it's -9. What's that in centigrade? It's cold. I know it's -4 is -20. There you go, got the wrong one. But it's very cold. There were days we were working on site where our eyelids froze, which is really fun. Gives you an opportunity to take very silly photographs of people who cannot blink. if you want to play the game of who blinks first, nobody wins. Anyway, that's normally what our field teams look like, because it's usually fairly warm at the site. You do get temperatures certainly into the low 40s at the site during the summer, so it can be fairly grim. You also get other things at the site that belong there. And I'm extremely aware of the wildlife around us. And that's something which we love to engage with. I have to admit, the grizzly bear's not my favorite thing. I've only tracked one on the site, and I don't particularly want it to come back. We did count our students afterwards. We think they were all there. Anyway, the scorpions aren't meant to exist this far north. And we kept being told by colleagues, you won't get scorpions. And when you've had 2 or 3 crawl down your back, and when they sting you, you get a baseball-sized lump growing. It's quite grim. The black widow spiders up on the top left, you've got to avoid, but everything else is fairly benign. But I always wonder, is anyone here from the US? Thank you. Can you explain this sticker to me, please? Because how do you do that? You know, what is this person here doing? We don't put these stickers on diggers elsewhere in the world. I've got things I have to learn. But anyway, it's very helpful. And my favorite one is we have buckets which we carry all of our dirt from where we're digging. And it's a big sign on it. It's basically got the bucket over the head saying, don't do this. So what do all the students do? Anyway, let's move on. So we move quite a lot of dirt at the beginning of most digs. And it's using techniques which have changed a lot with the advent of hydraulics. We move sometimes thousands of tons of what we call overburden. We've got to be careful because sometimes, or I should say the digger driver in that digger, his name was Kevin, as in Minion, but Kevin Jurassic. Spelt with a G, but I didn't care. The best digger name I've ever come across. But these guys helped us clear the site. There's only 2 or 3 of us because we don't want any of our dig team there when you've got heavy vehicles because it's pretty dangerous. So we have to have extreme health and safety on the sites. And that's what we're doing. We're moving down to this layer here, which is what we could do with the heavy earth mover. But below this was a sweet spot, a small layer that was beautiful, a layer full of dinosaurs. And we're very happy about this. We discovered it back in 2015. By 2016, we had field crews playing in it. 2017, it was getting great fun. 2018, we had crews from Naturalis Biodiversity Centre in Leiden joining us, as well as groups from Nat History Museum London, our teams from Manchester. It's a phenomenal international dig. It's about collaboration. And it's a fantastic site. Now, like most sites, we use a lot of technology to map, which is quite simple. This hasn't changed in 100 years. We still use the same grid system that many people excavating, so you can map the position of bones relative to where they are in the site. So you've got an idea where the bones sit next to each other. Because when you're back in the laboratory trying to understand how did that animal end up where it ended up, excellent mapping is really important. And you produce these lovely maps, which the poor person has to do all this mapping. It's a lot of hard work, but it allows us later to interrogate the site in ways that if you didn't have this information, it's lost. So it's so critical. This is why we get very worried when we hear people have found a dinosaur and have dug it up with their spade. We say, no, please stop. Let's help you dig it up. And then we can get information, adds value, the scientific value to the process. We can also use modern technology. That doesn't involve me. I let other people operate this machine because it's far too smart for me. What it is, it's a technique called light detection and range. It gives out an infrared light. So if I was to zap Pavel here on his birthday, and then I can time the distance it takes for the beam to hit Pavel, dissolve him a little bit, and it bounces back, I can work out how quickly that time of flight between Pavel and me, I've got a point in space I can measure, because I know the speed of light. It's quite easy to do, honest. But I can do that with every single person in this room, but I do it with every point across your body. You can reconstruct what you look like. It gives off about 30,000 points per second, and it allows us to reconstruct the site in 3D. So we can, again, investigate the site at a later date. This one actually overlays photographs as well. So we can look at where our dinosaur is. This is where the dinosaur's coming out. And with the high resolution settings, we can even see the bones, even the grain size of the material we're studying. And you can even see a group of geologists trying to hide. But we scan them as well. You don't want to be scanned because people can 3D print you. Think about it. Not good. But it's a useful technique for recording the site. And it allows us to map features, structures, which otherwise you might miss. Those white dots are trackways of animals. And they're sandwiched between this layer, which you can see the step here. That's where we get all of the fossils. And below is underlaying where we get all of the dinosaurs. It's a really thin layer. But on this lower layer, it's quite fascinating when you look at it in detail. You can see there's a big three-toed footprint there. That's going from the back of the footprint to the middle of the toe. You can see the other two toes there. So it's a big three-toed dinosaur walking across that surface. And any engineers in the room will recognize Rankine failure, Rankine zones, which are displacement rims. It's the same way if you don't put your foundation deep enough for your house, it will fall over, sort of thing. But this is the displacement which occurs as the animal walks over it. I love this stuff. Anyone remember vinyl? It's back again, apparently. Vinyl, when your stylus bumps over the vinyl record, it plays back sound. It plays it from the bumps and grooves that you have on the vinyl. This has potential not to play back sound, but movement. And we can use trackways to better understand, especially when you're using techniques like LiDAR, so we can work out the pace, the hip height, and calculate even the speed at which these animals are walking. But it's fascinating with this particular succession which we have at the Jurassic Mile. It's a watering hole. And it's fascinating. Now, if you're in the watering hole, you're all up to your necks in water. Now, if I'm a plant eater, my daughter's a vegan. That's hard, you know. Do you know how hard that is? I love it a bit. I'm a vegetarian at home now. I can't have any meat. Anyway, I won't go there. But my daughter would, as a vegetarian or vegan, that's a choice, I should say. But herbivores walk along the edge of water holes because they've got one eye looking this way, one eye looking this way. They've got maximum field of view around them. They would never do this because that's silly because you're exposing your rear to something that might attack you. So if you look at water holes today in Africa, it's fascinating seeing most plant eaters have this behavior as well. Predators, they tend to have lines that run at an angle straight to the watering hole. Either A, they're about to chase down something they're going to eat, or B, they don't care. They don't have to worry because there's nothing to eat them. We see the similar distribution of tracks at this site, which I think is pretty cool. We also get some three-dimensional tracks. This is where the animal's foot is squished down through sediment. And you can see with the top of the footprint, which you find, and if you keep digging down, you even reveal the pad at the front of the toe as it squished down into the sediment, affected that lower layer and pulled the foot up. It's not a very good photograph, I apologize, but there's a three-toed footprint there, which has been squished down from the upper layer. Again, that gives you an idea of what we call kinematics. Now, if I walk around like this, it's going to have very distinct ways of how force goes through my legs and makes very stilt-like footprints. If I walk more normally, I have a heel-down, rotation, toe-off phase, and it changes the way I put force through my legs, and the load on my foot changes as a function of that. So does the shape of your footprint. These footprints really can play back movement. Maybe not like that, but anyway, I'd love to see the tracks of John Cleese, but maybe not today. But we can do tracks now because we use a technique where we use gaming technology. It's a technique we call stress-constrained multi-body dynamics. There's a mouthful for you. What this allows us to do is create three-dimensional models and place them into a physics environment where all of the laws of gravity are going to work. We can get our animals, get them moving again. There we go, come on. And our T-Rex is rather complicated here. I don't know what he's doing with his hands. I think he's playing the piano. But the sauropod, that's Argentinosaurus, and we got that one moving. But what's fascinating, as techniques like this develop, we learn more and more about the biomechanics, how these animals once lived. and the techniques we're now deploying are not just being used by us, but this is being used in robotics as well. Then you can see how rapidly robotics is evolving. But the two fields running together, we can learn so much about extinct life as we can about maybe things that we can be using in our present and future. In terms of LiDAR, it's not just small areas we can scan. This is the side of a mountain in Spain, a place called Fumania, just north of Barcelona, near a little town called Berga. And you can see the footprints here running across. These are giant footprints of, again, sauropod dinosaurs. Now, I tried abseiling down this slope. It's pretty steep and it's dangerous. And not only is it dangerous, you actually damage the very footprints you're trying to study. So by using a much longer range LiDAR unit, we can capture a whole mountainside. And then we can understand something about the movement of these dinosaurs, in this case, from the late Cretaceous of what is now in the Pyrenees. It's the Tremp Formation, if any geologists present. It's a really wonderful place to be working. And just off the edge of where these tracks are, there's an amazing dinosaur egg locality as well. It's a stunning place to go. But it can tell us a lot about behavior, possibly. The problem with trackways, everyone goes straight to this, oh, we've got lots of trackways together. This is gregarious behavior. Because we do see it in the descendants of dinosaurs, the feathered dinosaurs. I think you call them birds, maybe? I don't know. I just call them dinosaurs. They are avian theropods to me. But the behavior we see in birds today is probably a good indicator, but you've got to be careful with trackways, because you might just have one mischievous dinosaur continuously walking in a loop, saying this will confuse them in 66 million years. Let's just keep walking like this. Yeah, they'll think it's a herd. Silly people. Oh, people haven't evolved yet. Oh, well, never mind, I'll keep doing it. You know, it's hard to say the timing of tracks. That's the problem. But let's take us back to the Jurassic dig. So this is what a dig looks like. We've got a lovely team working down here. That's our lower quarry, which is this pond-like deposit, which is wonderful. You go up past our shipping containers where we store all of our materials, and we pass on the road here. There's a dinosaur that was sticking out, bones out of the road, so we called it Roadie. Anyway, but moving up to the main quarry, this was a channel sand, though. Different environment, a channel sand. And the channel sand is where the heavier materials dropped out of the bed load of the river. In this case, it includes some dinosaurs. Now, you can see the people in the background. Oh, no, they've gone. There was a white cast there in the picture. It was about 2.2 meters long. About. It was 2.2 meters long. Reach over onto your back. Feel your shoulder blade at the back. That's a scapula. Your scapula is about yay big. That was the scapula of a dinosaur. About 2 meters. The animals at this site are vast. Oh, there's Yellowstone in the background. Isn't that lovely? You are in the middle of nowhere. And I love that. Oh, by the way, never ever buy a car rental, ex-car rental in America, because the chances are I have destroyed its suspension in the field. I know it says do not drive off-road, but I think it's more of a suggestion. Anyway, but it's, don't buy them there. We do use some quite heavy lifting gear on site as well, because the bones genuinely do weigh hundreds of pounds in some cases. And I know one of the dinosaurs, I can't tell you which because it's top secret, so I'm telling everyone. No, but one single femur of one of the dinosaurs we're getting in the new museum weighs 400 kilos. Think about that. Now, which bone in your body might weigh that? No bone in your. If a bone in your body weighs that much, go and see the doctor now. But this is the ways in which we've been moving these out of the field for many decades. And again, you can see some of my colleagues here who've worked at Naturalis Biodiversity Centre will recognise some of your colleagues here as well. So again, it's a wonderful international team. I'm going to crush them with a dinosaur. That's what we're digging up. And each year we would fill in a red dot on our skeleton as to which bones we got year by year as you piece together these wonderful creatures. Now, it's interesting, people have been digging dinosaurs out west for over a century. And the techniques they're using really haven't changed that much because we still use plaster and burlap to wrap up our bones. Anyone here ever broken a bone? Horrible, isn't it? No, no. When you break a bone, you want to stabilize it, stop it from moving. They put it in a plaster jacket, and that's to allow the bones to heal. Now, likewise, our dinosaurs aren't going to heal, but we don't want the bones moving any more than they should when we take them from the field to the laboratory, which is why we wrap them in plaster, and that's a great process to protect them. And we still do field jackets today. We don't use horses, and some of these field jackets weigh several tons. The reason I'm stood a little bit further back at the moment is if one of the straps snaps, it can cut you in half, so you've got to be careful. We tend only to use students who've been naughty to work near this. No. But I always think it's lovely when you see something like this move. This is a diplodocid dinosaur we're lifting out. And this is right. Hamilton here, my ex-student, he graduated, don't worry, he's not ex because of what's about to happen. Once you graduate, you're dispensable. No, you're not dispensable. But he's a lovely human and is quite brilliant in the field. But we move tons and tons of field jackets every summer. And that field season, we did 3 months solid in the field, which is actually quite brutal. It's hard work. But we also look at fossils in ways that people might not think is being paleontological. All right, obviously, we're used to looking at things with visible light. That's how we use our eyes. It's great. But the electromagnetic spectrum is gorgeous. There's so much more we can use into X-rays, into ultraviolet, infrared. All these different wavelengths are really important for studying fossils. And some of these things sound really odd. In fact, if you go to the doctor and say, doctor, I've got moldy toff, they might send you away with some cream and it will clear up in a week. But these terms are really quite impenetrable sometimes, but each tells a technique, a way of studying a fossil. And we use many of them, and this is one of my favorite places, the synchrotron. Now, synchrotrons, if I had a glass of water, and if I walk around slowly, it's very boring, water stays in my glass. If I start running and start doing this and go whoosh with water, you'd punch me. No, you wouldn't. No, what it was, it would come out tangentially from me. The amount of energy I'm putting into me running around is what this particle is doing. And it's not going to spill water out on people. This is just the booster ring. Speeding things, electrons up to relativistic speed of light, just below the speed of light. Goes out into a storage ring, still traveling just below the speed of light. At these speeds, it gives off incredible energy in the form of X-rays. These X-rays we hive off into what are called experimental stations, often called a hutch. I always look for the rabbits, never found them. And there we go. And we have our intense X-rays hitting our object, in this case, the lovely Archaeopteryx. And a wonderful curator from Berlin who was with us was utterly terrified we were going to vaporize the Berlin Archaeopteryx, which was a little bit scary, I have to admit. But it was a beautiful fossil, and when we zapped it with these intense X-rays, what we're getting as a shiver as these intense X-rays hit the atoms that construct this organism. Each atom is kind of tuned in as a function of each energy represents each type of element present within this organism. We call it X-ray fluorescence. So just like a radio tuning through different... I was going to get my friend Mark to play his guitar tonight. You were all saved. Anyway, no, sorry, Mark. But in the same way that when you play a different tune on a guitar, you're giving a different waveform. Likewise, as we tune through, I used to love these radios. Anyway, as you tune through different channels, you get to radio calcium. Anyone listen to that much? Great channel. It's good if you like bones. Moving right through to radio zinc. Now, zinc I love. Why zinc so? Because the way life uses zinc is brilliant. Imagine if this is just one point, but you can map every single point across a fossil to find out where the chemistry sits. This is what we did with a rather old bird. It was about 120 million years old. It's one called Confuciusornis sanctus from Liaoning province in China. And when we look at the channel, which is at roughly 2 keV energy, we're nudging phosphorus at that energy. But at each different energy, it nudges out something, a different type of element. Now, this gives you copper, calcium, and zinc in color. Now, the calcium in the bones We all know why that's there. I don't need to say that, really. You got lots in your bones. And the zinc in the sediment, well, it was a volcanic ash. Lots of zinc there. But what is all that copper doing in the feathers? You know, there's a great quote by the author Isaac Asimov. If you've not read any of his books, you should. And it's great moments in science are rarely met with the word eureka, but usually by the phrase, that's funny. Because a lot of science, you're not actually looking for it when it happens. And this is one of those cases. We were scanning this bird, and you go through tune through each channel now. There's chlorine, or cut now through to sulfur. Lots of it in the feathers. No surprise. And there's the calcium in the bones, iron, lots of it in that sediment. But it's when we get to copper, it's the brighter, the richer it is. And we had to find out what it was doing in the feathers. And we had to study modern feathers to work that out. When we did, we realized that the copper was in fact related to a particular group of compounds called melanin, pigment, color. Well, color's complicated. We'll get to that in a bit. But we can also study injuries of dinosaurs, and we'll see some from the Jurassic Mile in a second. This is a rather sorry-looking dinosaur that stubbed its toe, and this is the bone that it stubbed. This is what you call a fracture callus, and this is where the bone is regrown. That lump on the top shouldn't be there, and that's because the animal had at some point cracked its toe, and this is the bone's reaction. It's healing. What is fascinating, though, we can look at the chemistry of healing of dinosaurs, and these different colors correlate to different chemistry. And we can map how copper cofactors, which are critical in healing broken bones, forming that first sort of plug, which is of a rubbery material that's not yet bone yet. What do we call it, anyone? Cartilage. It's like cartilage or, it's that type of material. It's not true bone, you're right. Then we start seeing another wave of chemistry coming in. There's zinc. Zinc is critical in the formation of bone. There's these little cells called osteoblasts that love zinc. And they use this as part of the process. And as they're repairing the bone, they leave traces of zinc in the bone. And last and finally is the remodeling bit where you're finally healing. That's strontium. Strontium is the element used there. And you know what's really cool? If any of us had a similar injury, it could possibly kill us. The immune system in dinosaurs is phenomenal. The fact we can unpick the process by which the bone heals, we can start measuring how the animal fought such vile diseases in some cases, is amazing that we can do that in something that was alive, in this case, 150 million years ago. You think even with some of the best preserved dinosaurs, we can find out more. This is a mummified dinosaur. Have you ever been to the American Museum of Natural History in New York? Famed for the night at the museum. Of course, you walk in the doors of it and you realize nothing was filmed in that museum. But anyway, it's a phenomenal museum. I had great fun working there for a couple of years. They're lovely people. And this is one of my favorite fossils. It's a mummified hadrosaur, one called Edmontosaurus annectens. It's from that wonderfully named Hell Creek Formation. Now, it was discovered over 100 years ago. And the Sternbergs, who are an amazing family of collectors who dug it up, were genius at preparing these things. They took most of the matrix, the sediment, away from this mummy in the field. And there's preparators today who still don't know how they managed it. It's a wonderful job. I was involved with a gentleman who discovered a mummy a few years ago. It's one called Tyler Lyson, lovely chap. And he found this on his uncle's land. And you can see a tail coming towards us here. This here is a leg. That's an arm over there. Honest. It's of one of these creatures. It's another hadrosaur, just like the AMNH one. What was fascinating about this one, though, it was relatively inflated still. It was remarkably preserved. Skin was incredible. So we decided to speak to our friends at NASA, who allowed us to use one of their really big X-ray scanners that doesn't just produce one X-ray giving you a bulk sort of density of the object you're studying. It allowed us to do slice by slice. It's an enormous CT scanner. It was interesting, after we did this CT scan of this huge block, they were able to scan a wing of the space shuttle, which a few years earlier, when taking off, had had a block of ice hit the leading edge of the wing. And they were worried it wasn't going to make it back after its mission, but it did. And this wing had sat in the back of this cell for a CT cell for a good many years because they'd never worked out a way of scanning it. But the technique we developed here allowed them to scan that wing for the first time to understand the internal damage to the wing. I should have had spacecraft to the talk title. Bother. There we go. But, and it was lovely. Jeff Anders here, who's head of the CT unit at NASA, I remember he said very kindly to a National Geographic film crew, and I think he didn't like saying this, that dinosaurs are helping put people in space. Woof. That's a quote. Anyway, but this is one of the CT scans. Now, the skin is rich in iron, and that's what this envelope here, you'll see it changing as we go through. And so you could map the skin relative to the skeleton of this animal as we CT scan it. That's just the tail block. And you can see the little sharp bits of the bright spots appearing are nails, which are iron, and they stick out rather. There's another from the palate. So we could understand how big the muscle mass was around the tail. Why do we like that? Because it's like lifting up the bonnet of a car, looking at the cubic capacity of your engine. That's your engine as a dinosaur. Most of the big muscles are sat, sorry parents, in your bum. Because they're the big, does your bottom look big? Yes, because I'm a dinosaur. Because the dinosaurs have these huge muscles, which are called the cordofemoralis longus. They're attached down the tail and attached to the limb bones. And this big bulk of muscle, it's hard to measure, but using this technique, we could. So it allows us to make much better predictions on the locomotor ability of these animals, using, again, our computational modeling techniques. Have you noticed how dinosaurs walk on their toes? This is me in a CT scan. There we go. No, it's not. That's the only way you can, that's how dinosaurs walk, tippy toes all the time. Oh, that hurts. Oh, need to stretch a bit more. But they walk on the tips of their toes. But we walk plantigrade. The astragalus and calcaneum that form our ankle is fused to the end of the tibia of these animals. They walk totally different. The only animal that walks like dinosaurs today is modern dinosaurs. That's right, birds. So the birds can help us a lot, but they don't have tails. So that's the problem. When you don't have a tail, you start moving completely differently. So the only way to understand how dinosaurs moved is through modeling them like this or building very silly robots that are very expensive. I go for the modeling. Now, some of the X-ray techniques we've been using, is Tristan here tonight? Toad, he didn't come. Anyway, there we go. It's one of my colleagues who's a bit of a whiz with X-rays. And that's, well, he is here, a picture of him. That's Tristan. He also works at the museum. And this is Tristan in his natural environment. It's like a little cave, a cave made of lead, because he produces intense X-rays, which allows him to study the bones of these creatures, pterosaurs. And a few weeks ago, we published a fun paper because we realized if we could get ultra-high resolution scans of the bones, the wing bones of this little Rhamphorhynchus, we were able to see for the first time, you can see these little dots in this scan here. That's a normal CT scan. But if you work with Tristan, you get this CT scan. And this, we can see structures, which are called Haversian and Volkmann canals. They're wonderful. But we can resolve them for the first time. We've now printed it in titanium. And we've created a new material that our aviation partners is now developing. It makes aviation parts lighter and stronger. So we're inventing this new field of paleobiomimetics, we've decided to call it. But it's fun, because it has huge implications, A, for making flight safer, making aeroplanes stronger, but also reducing huge amounts of carbon as a function of lighter planes equates to less fuel spent, keeping it in the air. So I think there's many things to be learned in a Natural History Museum, not only about the past, but potentially about the future too. Which brings me to, what else can we learn about things when you bury them in the ground? Now, if I was to ask you to run an experiment for 10 years, you'd say, well, that's a long time. I might be doing something next week. If I said 50 years, you'd say, go away. Or maybe something else. If I said 1,000 years, you'd be laughing. 1,000,000, you'd say, you're bonkers, go away. We can't run experiments for that period of time. But the fossil record has already run those experiments. We have time-stepped samples going back in time that can help us understand what happens when you put something in the ground. Imagine you've got nuclear waste or some other nasty material you want to put safely in the ground. If you want to tell your children and children's children that it's safe, you've got to understand this process, what we call mass transfer, what's going to move out from that system and move into it. That's where we can use studying fossils in the past to help us. And to show this, I thought, this is my explanation of how Archaeopteryx might have become a fossil.
In this basic experiment called Dead Chickens, we can find out how hard it is to become a fossil. And in this case, it can be pretty stinky. And oh, gee.
How long is this rotting now?
Too long. This is what happens when you leave a body above ground.
Oh, yes.
And the stench is... It is quite disgusting. When you're above ground, the processes of decomposition kick in fast because there's a lot of other beasties trying to help you. And actually, this is making me gag. It's disgusting.
It's all decomposed.
Let's have a
And
look.
that's 2 weeks' time only.
And look, this is the skin. Oh,
No
the
more in
maggots.
place. Yeah. Look here, maggots.
Sorry, anyone still hungry?
Well, the chances of this thing getting into the fossil record are astoundingly slim. There's more chance of actually my stomach contents getting into the fossil record at the moment. Oh. Experiment number 2 is clearly going to show, we hope, how you can make a fossil. And this one has been subtly different from the first experiment, insofar that this animal has been bathed in damp, soggy soil for about 2 weeks. What is really interesting, you can see where already some of the decay gases have pushed up through and ruptured the top of the sediment. So we already know this is going to be pretty stinky. Let's let him out slowly and see if we can see what's going on. It's like making perverse sandcastles, you know that? Oh, jeez. Bloody hell. That's an interesting aroma. It doth protest.
Oops.
Oh, that's looking interesting. Well, that's look. Oh, wow.
Here comes-
Oh, jeez. I've got a mouthful of that.
I could have done the experiment here
Right.
tonight.
very soft and soupy, but you can feel the bones inside.
The bones are still
intact, yeah?
The process of mineralization can begin before the whole thing has started breaking apart. And this is exactly what happens in Zonhofen with the Archaeopteryx. It's in an environment where the usual bugs and creepy crawlies can't get to it. Let's see what it really looks like before I add to the mess. I just got some of this earth in my mouth.
Here you can identify still a chicken.
If that's what your chicken looks like, you've got one sick chicken. Right.
But the experiment clearly shows that this holds much better.
It's
in shape,
slowing
yeah.
down the decay process. So when it does finally collapse and it's got sediment over it, it's going to go like that against the sediments. That's what we see.
This is what we see.
If we're going to take a bet on these two animals, this one will have a much better chance of making it into the fossil record than the earlier candidate. So, experiment 2 is going to make it into the fossil record.
Exactly.
We have a winner. The second chicken did cross the road and became a fossil.
Here you go. I saved you from the smell. It truly was, the sound effects were real, I promise you. But we do experimental studies so we can reconstruct past environments. Because if you want to look at those dinosaurs at the Jurassic Mile, we use exactly the same techniques, understanding the chemistry of the sediments and the types of signals, markers that allow us to reconstruct the past. So now this is what the Jurassic Mile would have looked like 150 million years ago. And you can see the carcasses rotting away, as my friend Dino Frey would say. And it allows us to get a better understanding each year as we see cycles of sediment building up on this pond-like environment that seasonally would have filled with waters, which should have helped cover some of these animals. So it's how we can reconstruct this past and understand those burial environments. It really does help us understand how we can put things in the ground today to think about where they might disappear into in the future as well. But once the dinosaurs get back into the lab, there's fun things to do with them. Clean them up for a start. That takes an awful lot of work with skilled preparators and conservators who spend many weeks and months cleaning up the backbones of these animals. Oh, that's a funny ringtone. I like that one. This one is where the animal's broken its tail. The two bones are stuck together. But if you look at the other end, what are those scrape marks? They're right at the joint capsule. Now, that's bite marks. There was a dinosaur that was chewing down on this one, but it wasn't just doing any old, let's just bite here. It knew precisely where to pop the joint capsules to pull the chunky bit of tail away. So it's butchery. It's amazing. And as the song goes, and I'm not going to sing you how the bones fit together, but you spend many weeks, months, sometimes years reconstructing these animals. And this is what we're doing at the moment for the Natural History Museum Abu Dhabi. Not this specimen, I might add. This is one that's in the Children's Museum of Indianapolis that we dug up a few years ago at the Jurassic Mile. But we are in the process of piecing together some wonderful things that are going to take your breath away. And I just cannot wait to bring you to the museum to see them. But I want you to leave with this message, though. When we look at paleontology, when we look at natural history, the type of science that we can do allows us to really answer some quite big questions about what you might want to do with, say, waste in the future, or even help us understand when there's an oil spill, how that oil is transmitted through that ecosystem, because any animal that's feeding and taking compounds which are from the hydrocarbons into their system, they often get dumped rapidly into things like feathers. We can measure hydrocarbon-derived porphyrins, we call them, but we can map the distribution of an oil spill as a function of a single feather. We don't have to kill a bird to do what we call a necropsy to learn how much of a particular spills got into this food chain. We just need a single feather that we can scan using the techniques we've developed at the Stanford Synchrotron and at Diamond. The same technique we've developed to study the color in ancient birds is now being used to study human brain slices. I work with a team of neuroscientists as well, and we're mapping the nucleation centers of particular compounds associated with potential diseases such as Parkinson's and Alzheimer's. We've got initially what we call the Healthy Human Brain Project. We've been looking at where people have donated their brains to science when they've passed away, and I'm fascinated by healthy people, because healthy people allow us to map a baseline of what healthy brains look like, because sadly it's usually pathologic brains which have had disease, that end up being studied. We need to have the healthy ones as well as the non-healthy, and that's helpful to study over here. If you want to learn more about what we do with dinosaurs, maybe you can watch one of these fun shows that we do occasionally, because one thing I desperately want is more people in this audience to fall in love again, not only with natural history, not only with the past, but to think this wonderful planet on which we live has an incredible future as well. And there are many people here who are going to be part of that future and hopefully work with us at the Natural History Museum Abu Dhabi to better understand the past, to impact the present, and have that fun future. Thank you very much.
That was quite a talk. I lost my words. This title? Talk.
I'll go. Great. I'm running.
Good. Perfect. I'm sure there is plenty of questions. If you don't mind.
If I sit down, I'll sleep. I don't. Do you mind if I stand? I got back. I was in South Dakota on Monday, and I got back at 8 o'clock last night. I've done 30 hours on an aeroplane yesterday. So if I sit down, I'll fall down.
Let's have the first question. Who's starting? All right. Yes. Can we have...
Oh, I should do it, shouldn't I? It'd be even more fun. Oh, there you go.
So my first question I find very...
Your first question? Hang on. You're one of those double questioners, aren't you? Go on then.
Yeah.
So my first question is, do penguins also relate to the dinosaurs?
They do. In fact, my favorite PhD project, you can actually probably Google this still. We put up a PhD project a few years ago called Mach 2 penguins. because I decided that penguins were such bizarre birds that they fly, they do underwater flight. The same physics that helps us understand flight of birds works underwater. In fact, the principle, Bernoulli's principle, was worked out through hydrodynamics, how things move in the water. But water is very viscous, and penguins are brilliant at flying through water. How mad is that? Yes, they're birds, but the loading on their wings is incredible. Birds that flap around in air is not very viscous, so they're very easy to go push through it. But penguins have extreme loading on their wings, and we calculated with a little bit of maths. Yes, maths is beautiful too. It really is. And it allowed us to see the loading on the wings of penguins was phenomenal. So we did a Mach 2 penguin project, because we realized that we could design new aeronautics materials looking at penguins. But penguins are birds. Funky birds, but they're birds. Lovely birds.
Yeah, I know that.
Yeah.
My question was more like to how did the penguins like all of a sudden started existing on Earth after the dinosaurs like
They
died
didn't
down?
exist. They through millions of years of wonderful adaptations to. I think the earliest penguins, if you can call them that, they weren't really penguins at that stage. There was a creature called Hesperornis and various other swimming birds that were back in the Cretaceous. You find them in the Kansas chalk and so on, if you want to go hunting for fossils there. And these are creatures that seem to be as much adapted to swimming as they were to flight. And we think they probably had the ability for underwater flight. When you look at something like a cormorant when it dives, they don't stop flapping when they hit the water. They keep flapping underwater. They can swim. They're remarkable. I think this is something a group of birds evolved quite. I've looked at penguins in New Zealand that are, I'm trying to think, they're Miocene, aren't they, Mark? I think they're about 7 to 8 million years old. I need to check on my earliest penguins, but the penguins in New Zealand are giant penguins. Now that sounds like a movie, but they were over 2 meters tall. So imagine a big penguin. But they're about as big as penguins could get. I think that's to do with hydrodynamics. But when they first appear in the fossil record, I'd have to double check. I'm pretty sure there's some ancestors in the Upper Eocene. So probably around about 50 million years ago, there's some beasties that have aligned to being sort of certainly related to penguins. There's a lady called Julia Clark who's been doing work on them. I need to call Julia. She's the expert on this. I need to call a friend. Sorry. Jet lag is kicking me like you would not believe. So do you have one more question? No, okay, that's good. No. Go on then.
Yeah. Does finding fossils from dinosaurs, does climate change like could get in the way in the future? Because climate change is like getting like warmer and warmer and warmer. Would that affect like finding fossils?
That's a good question.
It is a good question.
Or like making like fossils? Would they break them underground or something? Would they like all of a sudden disappear maybe?
I think you've almost answered the question for yourself. You're thinking about it a lot. Yes, in some environments where extreme temperatures, any fossils exposed at the surface, if those temperatures become more extreme, especially fluctuations in temperature through time, either through night and day or through seasons, that can impact the freeze-thaw or shattering of material through time. I could be careful how I answer this now, but there are lots of fossils in Antarctica that we can't get to because of ice. I'm not promoting climate change at this point, but so in some ways we'd see a lot more Earth. Greenland has got some pretty cool stuff as well. It's covered in the Greenland ice sheet. I think this about 70 meters sea level rise, if we lost all the ice, would probably cancel any gains we'd get from losing ice, and it would be a bit of a problem for the world. Climate change is real. I mean, it is happening. And I tend not to use global warming anymore because some points on the planet are warmer, some are cooler. It's climate change. It's very hard to model and to understand. But as we better understand it, yes, it is going to impact something like paleo, but I'm more worried how it's going to impact us as a species in the future. But there are things we can do about it. And that's why, again, we've got a Natural History Museum here in Abu Dhabi, so we can tell people that, this is still a wonderful planet, that there are things we can do to hopefully give it a much brighter future if we can make change.
Can I ask one more question?
I think we're gonna. Sorry,
Okay.
Ask me afterwards.
Yeah.
It'd be a big conversation otherwise.
because I saw one. Yeah, great in pink,
Behind
just
you.
here. Yeah,
Yeah,
you have
fire away.
you had your great. Get the not just behind, row behind, just behind you. Yeah. Wait, we can't hear you. Can you? Yeah.
Here you go.
ahead.
It's on.
It's working now.
Why do the fossils? How do you lift the fossils?
How do I lift the fossils? Well, I used to be 6'8", and they've just made me. I've lost a lot of height lifting fossils. We lift. Was it lift the fossils? Is that correct? Thank you. Well, we lift some of the smaller fossils. We very carefully move the sediment from around the fossil first, keeping a lot of the rock around the fossil. Because what you don't want to do is tidy away all of the rock to the bone, because if you start moving it, you can damage the bone. So you want to take a piece of the rock around it, or sediment, out of the ground with it. So you dig a hole around, you cover it in plaster, and you try and undercut it so that it's holding it. It's a bit like holding it like this in your hands. And the last thing you do is cut out the rock from underneath it, and you just wobble it, and you can lift out the fossil. Now, that's easy when it's the size of a head or something that's this big. When it gets to several tons, that's when we have to use machinery like you saw in the talk, or we use big diggers or cranes even to lift these large weights in the field. So we use lots of technology to lift, and ideally not our backs, because it can hurt. But good question. Thank you.
All right. Suddenly, on this, yeah, I'm just gonna go this way. And then I come back here.
Hi, first of all, thanks for the amazing talk. It was really interesting.
That's very kind.
I had a question. You keep on calling birds dinosaurs, like flying dinosaurs. Is there a particular point in the whole timeline where the dense bones and the kind of hollow bones which birds nowadays show kind of bifurcated, or then it started becoming more differentiated into something that can fly, something that can walk, probably?
What a great question. Thank you. I like that. That's a great question. Predatory dinosaurs, theropoda, literally meaning beast foot. This group of animals, even when we look at their earliest ancestors, into the late Triassic, into the lower Jurassic, they had hollow bones. The avian lung, which makes birds so amazing. It means that, you know, when you're climbing up Everest, you see a bird fly past you, and you're kind of going, can't breathe. I've tried, it hurts. And it's very annoying when you see a bird going, going past you. It's because they've got this remarkable avian lung. And we see evidence on the anatomy of the rib cage of dinosaurs that they too had an avian-style lung. And we even see holes going into the hollow bones, which is part of the respiratory system, which is why they have these hollow bones. And there's air sacs distributed around the body of birds, and we think there's evidence to support the same air sacs in predatory dinosaurs. So there isn't a huge leap to take. Now, the earliest feathers, there are some fossils, certainly from the late Jurassic, such as Archaeopteryx. There's new ones which are being found in China as well, which support the presence of filament-like structures in proto-feathers, not quite functional feathers, but there's some which look like feathers from today. The feathers of Archaeopteryx are asymmetrical. They're like flight feathers you'd see in a modern bird. So many of these adaptations we see for birds are present in early theropods, but by the late Jurassic, you've got Archaeopteryx, which is basically a bird with a long bony tail, or a dinosaur with feathers, I should say, because Archaeopteryx still has socketed teeth. And it has many characters that make it a dinosaur. In fact, if you don't see the feathers preserved on it, you might think it's a relative, Compsognathus. It looks like Compsognathus. It's not. It's a bird. And all this idea that Archaeopteryx couldn't fly, they've even CT scanned the brain case of Archaeopteryx now. And it shows it's got the similar layout of an avian brain. Not quite that we see in modern birds, but we can see this beautiful lineage then from Archaeopteryx right the way through from creatures like Sinosauropteryx from China, Confuciusornis. There's a whole lineage of birds now which help us map this evolution from non-avian dinosaur to avian dinosaur. And that's where the fossil record from China has particularly helped answer those questions over the last sort of 30, 40 years. So it's been a really exciting time to be a paleontologist. You're welcome.
Yes, we have one question here.
Actually, is that the two-question gentleman there? It is. I'm waiting for you. Sorry.
All right.
So, yes.
I can't tell if the microphone... Oh, it's working. All right.
Yeah.
Anyway, I'm very logic-based, so I like to study stuff like this and really learn about history. But part of the problem I have with it is that with most history is that depending on which country is teaching the history, the story can change. Yes. What I like about paleontology is that everyone agrees on it, because it's not like a historical event that involved different nations, so there isn't any bias that changes the story. It's like, it's pinpointed. The whole world can agree on paleontology. That's what I like about it. But as the study progresses and we learn more and more about dinosaurs, but also the dinosaurs' genetics. So my question is, do you ever have concerns about maybe Jurassic Park becomes a reality, or we become so scientifically advanced that we somehow manage to bring animals from extinction, or perhaps create completely new animals that were never meant to exist?
I think I totally disagree with you. I'm joking. I just wanted to disagree.
Right,
Sorry, just following your line of thought. No, you're right. Jurassic Park. Is Jurassic Park possible? First, I would say that most paleontologists are sensible folks, evidence-based scientists. They don't always agree, I'm afraid. I wish they did, but you know what? I love it when people don't agree. That's when we learn things. I love getting things wrong as well, because when I get things wrong, I learn. I tend not to learn when I get things right. So having arguments and stuff, it's not arguments, we call it debate. It can be quite vigorous. Some might call it argument, but it's healthy sometimes for a science to have that. But I'm so pleased you see that, because I'm frightened sometimes that some people see science as this mudslinging match sometimes. It really isn't. It is quite beautiful. But in terms of your Jurassic Park question, can we genetically engineer a dinosaur? Yes. Will it be a species that is from the past? No. It's not very difficult to tweak the genome of, say, a ratite, emu, cassowary, ostrich, tinamou, one of the small ground birds today, because you haven't got much to do to tweak the genes that, say, produce these feathers to make it more scaly for the rest of the body, even though many had feathers. And then that gene responsible for socketed teeth, you could turn it on. There's an old saying in the UK, as rare as hen's teeth, and that's where the gene, when during development, the embryo is exposed to specific chemistry that turns on that particular gene that permits socketed teeth, so you get killer chickens from hell. Anyway, but so in the genetic package of birds is information to genetically engineer a dinosaur. It would be astoundingly lonely, but you could potentially do it. Should we do it? No, because we're creating vectors for viruses and all sorts of things. We don't know how these organisms would interface with existing pathogens on the planet today. I think it's foolhardy to bring something back from the past for that reason, because you could create a vector for the next big pandemic. And that's why we're toying enough already with our planet's sort of natural history. I'd rather be saving natural history rather than to create something that is very unnatural history for me. So that's my take on it. There's many who feel that de-extinction is a way forward, and maybe. in some recently extinct species, we won't risk this potential danger that such an organism might bring. Is it possible? Yes. Can we bring a dinosaur back from the past? No. DNA is a water-soluble molecule. It breaks down roughly between 1 to 1.5 million is some of the oldest decent DNA we can get. You might get fragments of DNA, but not enough to reconstruct a dinosaur. Proteins, you might get. There's some recent publications saying they've got collagen found in dinosaur bones. Now, every time this has been published in the past, the team I work with has rerun all of the analysis and found it was contamination. And it's amazing, you get the big headlines when something is, oh, we've made this discovery, when someone says, actually, no, it's not right. No one reports that, which is a bit annoying, really. But so I'm still not convinced we'll even get some of the more robust biomolecules like collagen, which is a triple helical molecule, very tough, that it doesn't survive the ravages of time. So yes, we can bring dinosaurs back, but it would be a new dinosaur. It would technically be a dinosaur by the characters and the skeleton and what it looks like, but it would be a new species. It would be a genetically engineered one, and I'd rather not do it. But a good question. Thank you.
Thank you.
Thank you.
Right, I'm gonna go back. Go back that way. Yes, go ahead.
Hello. So I'm just wondering, how does technology to discover fossils work for oceans, and how does that work for, I guess, marine life to discover that evolution?
It's funny looking at marine organisms. First, we do actually go hunting for fossils in near-shore environments. I've gone diving or surface diving looking for fossils, especially where I know a particular geological formation pushes out to shore, and you know no other collector is going to be mad enough to do this. So you swim out and dive to find fossils. It can be done. Ideally, you need nice clear waters. When I tried it on the Isle of Wight, it was like diving in mud, so I didn't really see much. So you can find things in there. A lot of the technologies that we deploy on land are sometimes quite hard to deploy in a marine environment. There are some of the techniques we've been developing, certainly when we're looking at the stress-constrained multi-body dynamics. We just had one of my PhDs finishing his PhD on the hydrodynamics of whales, for instance. And that's been a fun project, looking at the evolution of whales through time and how we can understand how what was a land organism moving back into an aquatic environment, the adaptations and the chain of events that occurred to allow it to become efficient swimmer as extant whales are today. So we can deploy some of those technologies. And likewise, when we're studying the uptake of chemistry from pollutants and so on in the environment, when the Deepwater Horizon spill occurred, gosh, it's nearly 10 years ago now or more, in the Gulf of Mexico. Sorry, I wouldn't say that loudly. But there was a big... Be good, Phil. Be good. No, so there were quite a few animals washing up which had had a rough time. And I tried really hard to get some of the dolphins which had been washing up. Right, dolphins are mammals, but unlike most mammals, what don't dolphins have? What did I used to have on my head? Hair. Now, when you get a toxin in your body, you can throw it out to your fingernails. We'll pick it up quite quickly. You dump it into fingernails, and your hair is a good way of the body dumping it into keratin tissue, because keratin, which is what is made of, is really good at hugging onto quite unpleasant trace metals and so on. So we're good at dumping it into hair and into our fingernails. So we decided dolphins can't do that. So maybe this is what's killing them during the Deepwater Horizon spill. And we wanted to get hold of a dolphin when it was sadly passed away, freeze dry it, serially section it, take it to Stanford where we're working at the particle accelerator there, scan each individual slice to see where the chemistry was going into the organs of the body of this particular animal. But we weren't allowed to do it. It was stopped. So all we could do was we collected brown pelican feathers along the shore, and we did the study on that. And over a period of 10 months, we were able to map the uptake of hydrocarbons into the feathers, because it's the same process. When the calamus is growing within the skin, it's still fed by blood, and the blood takes some of these trace metals from toxins from the environment and dumps it into the feather. So the feather is a record then of trace metal loadings in that particular feeding regime for the brown pelican in that case. So there are ways the techniques we develop for studying fossils can be deployed for studying marine life, not only the birds, marine birds, but also marine mammals. And one of my PhD students is working on collagen in fish as well, and looking at how that can tell us much about the biology of these particular organisms. There's so many things we can deploy using imaging. And that's, I should say, why the Natural History Museum Abu Dhabi is building state-of-the-art imaging labs so that we can do the type of science that I'm talking about today here in Abu Dhabi. And that really excites me, especially when getting a good question like that, because maybe you can join us at the Natural History Museum and help us explore science like that in the future.
Thank you.
How exciting. All right, I'm going to take 2 more questions, and I'm going to go for over there. Yes, go ahead. Yes. Do we have, yeah.
Oh no, that's good. I will have to take his question next. I feel guilty. Before you say anything, one question.
One question.
And
yes,
I've listened
so
to your questions for the last couple of year or so. Please come and talk to us at the museum.
Okay.
I would love you to come and work with us in some way. Right, you can pass the mic now.
I have one scientific question and one just a non-scientific question. Okay. First of all, you mentioned that there are plenty of fossils in Greenland, Siberia, Antarctica, but like, were there any dinosaurs that did live in those colder climates?
Good question. When you go back to the Mesozoic, which is the age of dinosaurs, the Triassic, Jurassic, and Cretaceous periods make up the Mesozoic. That's roughly from 251.9, roughly, anyway, to 66.1 million years ago. That's the Mesozoic. At this point in Earth's history, it was a greenhouse planet, no ice caps. The configuration of the continents was very different today, and it was possible that you could travel from South America through to Antarctica at that point in time. There was no circumpolar current at that point. Antarctica hadn't broke away from that landmass. It was part of a much larger landmass called Gondwana, which was Africa, South America, and Antarctica. So it was a very different configuration, and there was possible for migration. I know you're about to ask me, what about the winter? Because it would go to a point in the year where everything goes dark, it gets pretty cold. Even in a greenhouse planet, it would have been cold, and plants don't like it. So the chances are we have migratory patterns of dinosaurs moving into some of these areas and moving out. And there's some wonderfully named dinosaurs from Antarctica, including the cunningly named Cryolophosaurus. Yes, ice lizard, whatever. There's some really fun ones. There's Lealanasaura, there's various other strange, there's even an Arctic allosaur, which is probably an ethymimid, I don't believe the taxonomy, but anyway. But the nice thing is there are fossils there. So it does show there's actual evidence they did migrate into Antarctica, but there was a land bridge that allowed them to get back into slightly warmer climes when it was not the Arctic winter. But don't think deserts of ice. It was a very different planet. If you're up above Earth during the Mesozoic, you wouldn't see an Earth that you would recognize. So there you go.
I have one non-scientific question now.
Oh,
a very
right.
short one, then.
Also, I want to mention this is the very first non-scientific question I've ever asked in a talk. Oh yeah. What is your favorite dinosaur? I don't know. I just feel compelled to ask. I'm just curious.
That's like asking me to choose one of my children. It's not a dinosaur. It's a modern animal. It's a pangolin. And that's not a dinosaur, it's a mammal. But pangolins are just awesome.
Pangolins are cool.
Pangolins are very cool. But if I had to be pushed for a dinosaur, it's the one which I opened up a book when I was a little bit younger than you, I think. And it caught my imagination. And I remember going to London and going to look at the London Archaeopteryx when I was a kid. And I was just completely blown over by this beautiful fossil that I worked out that I could fit in my school satchel and run. Could have been mine. But I've been lucky enough to work on most of the Archaeopteryx that have been found. and I think it's one of the most beautiful fossils. And if I was to choose one, that if you're willing to buy it and put it in my living room, I'd be very happy. But no, it belongs in a museum, but it will be Archaeopteryx. Thank you.
Amazing. I think we're going to stop on this one because I think it was a nice one. And
fall asleep.
Yes. Thank you a thousand times, Professor Phil Manning, for this amazing talk.
Thank you.
Great title, amazing talk. Yes, indeed. Thank you for being still standing in front of us. Thank you, everyone, for those amazing questions and that great audience. As usual, we'll see you next month. Please keep an eye on the website. You'll have all the announcements soon enough. In the meantime, please, I wish you a great Ramadan, and there is a Eid celebration coming up. Happy holiday to all the kids, or most of them, I guess, and see you soon. Thank you.
Shukran.